So if you guys remember, right, an instrumental variable is something unique that's going to let us understand the causal effect of a variable. And the most critical thing about an instrumental variable is that it affects the outcome that you're interested in only through the treatment variable. Okay, and as far as the implementation of it, we use something called the two-stage least squares. Okay, so who remembers from last time how that works? No one? Okay. So then we'll do a quick refresher. Right, so our general thing is, oh, out of batteries already. 1 second. And we're back. Okay. So remember our causal diagram looks something like this. U, X, Y. So we have this issue where I would have a hard time talking about the causal effect of X on Y because you've got these unknown, unobserved variables that could be influencing things. And so we want an instrumental variable that affects X and it affects Y only through X. Okay, so we estimate this using two SLS, two-stage least squares. So stage 1 is where we do our treatment variable. We run a regression of our treatment variable on IV plus all the controls, and then you've got your error term. Once you've calibrated this model, I can then predict my X hat, and then in stage 2, I can do Y is equal to beta times this plus all my controls. Okay. And by doing this process, the only variation that we see here is due to what? It's only due to the instrumental variable. Okay. Okay. Any questions about this? So, okay, let me, before we show the implementation, I do feel like IVs are maybe a little bit confusing to think about in this abstract. So let me give a more concrete example. So this, okay, when you think about so there's an example from a paper that I published a while ago, where we were trying to figure out the effect of gas prices on VMT. So VMT is how much you drive. Okay, and so if I have a bunch of observations about how much people drive, and I have a bunch of observations about gas prices, right? We might try to do this causal diagram thing. But there's like all these other factors that relate to how people drive. And that could confound any conclusion that I would have if I were trying to run a model that was like VMT is equal to beta gas prices plus all my other stuff, right? So like, what is something that could affect how much someone drives?
Infrastructure.
Okay, yeah, infrastructure, anything else? Sorry? Okay, like distance from work, yeah. So if you have like observations about VMT and observations about gas prices, but I didn't have observations about the amount of infrastructure for a particular person or how far someone lived from work, those effects may compound variations in gas prices that would affect my VMT, okay? So can anyone think of something that might affect gas prices but wouldn't affect VMT? And may not, and something, so, right? So what is an instrumental variable that affects gas prices but doesn't affect VMT, doesn't affect infrastructure, doesn't affect the distance from work, and doesn't affect any other thing? Yeah.
A war.
A war. Okay. Okay. So let me like put on my economist hat and think about like counters to that, right? Okay, so could a war affect? Oh, actually, there's a example of this from recently. So, would you say that the type of car you drive affects, or yeah, the type of car that you own affects how much you drive? So, if so, right, so the war in Ukraine affected supply side issues for production of vehicles, and that would change vehicle ownership, and so then, you know, that could in turn affect VMT. So,
Price of oil.
well, okay, well, hang on. So like, so I'll say, you know, whether or not what I said is true, like this is the thought process that you have to take to determine whether or not an instrumental variable is a legitimate instrumental variable, right? Because I'm like, oh, war causes these supply issues that causes this, that eventually leads to VMT. And what I'm demonstrating, right, is there's like a series of things that do that, and that's not allowed. You can't have that. And that's the most difficult part of getting a good instrumental variable. Okay, so in the paper that we wrote many years ago, the IV that we came up with. So I will also, I'll say very specifically, we were using a data set of VMT, VMT and gas prices in Pennsylvania. I did grad school in Pittsburgh. So, what we looked at were hurricane events in the Gulf Coast. So does a hurricane that happens in Florida affect how much infrastructure you have in Pennsylvania? No, probably not. Does a hurricane affect how far you drive to work? No, right? And so we could argue that these things are not happening. Okay, but we do know that actually when a hurricane happens in the Gulf Coast, there is a portion of the oil market that is affected because a bunch of refineries exist in the Gulf Coast area that get shut down when hurricanes pass through. So we treat hurricane events in the Gulf Coast as an instrumental variable that affects gas prices, but it doesn't directly affect your VMT, and it shouldn't arguably affect things that influence VMT, like unobserved variables that affect VMT. And if it truly follows this pathway and nothing else, right? So it doesn't do this and it doesn't do this, then you can argue that, okay, it's like a good instrument. Okay? Or sorry, let me be precise here, that it is a valid instrument. How good an instrument is actually is a quantitative measure related to this part here. Okay, so this is like a regression, this is kind of just like your beta. If that is like 0, it's not a very good instrument, right? Because it means that your instrument isn't, even if it's legitimately, in theory, following this schema, where it's like this and not like this, it still could be a bad instrument, a weak instrument, in that variation here doesn't cause variation here, in which case you don't have much to go on. Okay? So that is our concept behind instrumental variables. Yeah.
So it has to affect only one variable.
It has to affect the treatment variable.
Treatment variable.
The variable that you want to determine what the causal impact is on an outcome, right? So we wanted to know specifically, if you change gas prices, what happens to VMT?
You say it can also be bad if the effect is too low on the treatment variable.
Yes. So if variation in your instrument doesn't lead to good variation in your treatment, then it doesn't really matter, right? So the example would be, in this particular case, hurricane events happen, we know that they physically shut down a bunch of refineries, but what if gas prices don't get affected by that at all? Then it didn't really matter that there was a hurricane, and it didn't really matter that there was a refineries getting shut down, right? So we do want to see some variation on your treatment variable as you apply your instrument.
When you say some variation, what's the threshold? What is the criteria?
Yeah, there's like a statistical test for that. Yeah, oh man, what is the name of that test? I don't remember off the top of my head, but there's like a test that tells you, and then there's like a significance level. And
And if I may just in this example,
Yeah,
what if the gas prices did change?
yeah.
Is there a way to know, maybe it was not due to the hurricane shutting down the refineries?
Well, the idea is that you have all of your controls here, so it'll control for everything. Yeah, and we'll see that in the R example. So let me jump over to that.
So would you want more than one instrument in one model?
Ooh, you could.
Like, would you want all of your variables to be instruments?
No.
Okay.
No, okay, yes, interesting question. So, when you instrument, like, so I have all these other controls for like what things might influence VMT. But what the instrument is doing is letting you argue that you've like cut off controls for all of your unobserved stuff. Or you've cut off the effect of all the unobserved stuff. So you wouldn't really need to have instruments for all of your variables unless you're interested in the causal effect of like a whole bunch of things, which I've never seen. Yeah, that would be highly unusual because like typically your hypothesis in like a study is like understanding the effect of like one or a small subset of things, not like many things.
But if you have like a causal diagram and you say like, okay, these things are covered by this instrument and these things are covered by this instrument.
Oh, hang on. Yeah. Okay. Yeah. Okay. Hello? Okay, here we go. I see what you're saying. So you've got this. U x1, x2, x3, and y. So something like this. And you're asking, can I do this?
I'm not sure if that's what I had in mind.
Okay, who thinks this is a valid instrument? Anyone? So this actually violates our definition because it can only act through a single treatment variable. So if you wanted to do this, you would need to do this. And then you could argue that the betas on a two-stage would be causally identifiable. I guess this would be a four-stage because you're like, you would do one stage, and then the final stage. Am I interpreting your question correctly?
I think, no, I don't know, let's just skip it.
Okay. Yeah, if you were interested, so what I would say is like, more generally speaking, if you're interested in understanding multiple causal effects, I think most people would tell you to run multiple models.
Yeah, I guess what I was thinking of is like a dialectic acyclic graph where you have things that are influencing other things and you could cut off like a whole string of things.
Oh, yeah.
But we don't have to, we can discuss it separately.
Yeah, okay, sure. Yes, I think you can do that. Yeah.
Okay, I just have one question about
Sure.
your example of the instrumental variable.
Uh-huh.
Was it as simple as just like a binary of like was there a hurricane or not, or were you measuring like levels of hurricane?
No, just like, I think we focused on hurricanes that we knew caused refinery impacts, and then we just had like, I think there was one version of the model where we had just dummies for time periods of when that hurricane happened. And then in a different model, we had like a quantification of the actual refinery shutdown effect. It was like how much volume they were producing or like how long they were shut down. It's been a while, but something like that. Yeah. Instrumental variables don't have to be like super complicated or anything. They definitely could be dummy variables, but you always run the risk of like having a weak instrument, right? If the variation isn't lining up. Okay. So how do you actually implement this? So sometimes I show how to do this manually, and then we could actually run a first stage OLS using LM, and then a second stage doing an LM. And I think I will actually add that into our notes that I post online, but I'm not going to make us go through that today because we've got a lot to cover. But I will show how to run an instrumental 2 SLS regression. And yeah, there's a couple different ways to run 2 SLS. The way that I'm most used to is via a function called IVReg, which actually I'm not going to do today. We're going to show how to do it with the FEOLS function, which we saw last time for the fixed effects. It can also do instrumental 2-stage least squares regression. So this is a data set from causal data called social insure, and what we're going to do is, let me run this, take a look at the data. So, take-up survey, whether the farmer ended up purchasing insurance. It's a binary 0 or 1, and so we should be running a logistic model, but I'm just gonna straight up run a linear regression. And we have a bunch of characteristics of different farmers. And the idea is that we want to understand whether or not, where is it? The take-up rate prior to the experiment has a causal effect on whether or not they take up the insurance, okay? And the instrument that we're using in this particular regression is default. This is a default option in the experimental format you're assigned to. So this is actually almost like a natural, not even a natural, this is literally an experiment that can be run. So you know that the treatment effect for this is random, right? Because you can just randomly choose who to give the pre-take-up survey to. So, okay. I'm actually going to say it's a little bit less relevant. I think the primary part of this is to understand the concept of the IB and then see how to implement it. Okay, so this is our response variable, our outcome variable, and I'm going to add in all of these controls. And so the idea here is you kind of structure this similar to a linear regression, except at the end of this, I'm going to add in essentially the first stage. Okay, so I have a little vertical bar here that separates the first stage. So this is the x that will then become the x hat, and default is my instrumental variable. Technically, this will control for all of the x's in here, but it's structured in a way that you don't have to type it out twice. But really, what's happening in the first stage is default plus male plus age population plus rice area 2010 and so on and so forth. And there's a little extra thing. This example is a little bit more detailed. They have their clustering. So this is it's actually a fixed of x's on top of the ID, but don't really worry about that. The main thing to take away is vertical line, treatment variable on our instrument. That's how we structure these things. And I'm just gonna copy and paste the summary part. Let's run this. I need to type this somewhere. There should be an underscore on the tree. Okay. Yep. Friends, okay, so the effect of the pre-takeoff rate is this friend's purchase behavior thing, and this effect is what we would argue is causal. This has omitted all the other variables, but in the settings you could choose to show them if you wanted. But the whole idea is this effect, once instrumented, is supposed to be the causal effect. Okay. Questions? Yeah, so if I ran the example that I was giving, this first stage thing would be the effect of hurricanes on gas prices, and then this thing would be the gas price effect on BMT. Yeah.
Can you explain just one more time for the vertical line in the
Yeah. So, this would be like, in my example, my generic example, BMT regress on all the controls, vertical line, gas price, which is my treatment variable, regress on hurricanes, your instrument. So this is outcome variable, controls, vertical line, treatment variable, regressed on instrument. Yeah. Okay. We good? Yes.
Can you have two clusters? Can you have address
Mhm.
and state? Or
Yeah, definitely. So all the rules that we talked about before about fixed effects panels or whatever, like those groups, you can have, yeah, you could have two-way, three-way fixed effects, that's fine. Okay. Questions? Any other questions? All right, we're gonna do a pretty big pivot now. So the last two lectures have been focused on sort of causality, and the concept of causality is really centered around the fact that like I want to understand particular things about some kind of treatment variable, some kind of variable and its effect on the outcome. That is a broad class of regression and data analysis, right, that we kind of affiliate with like the broad area of like econometrics. Okay. Kind of on the other end of the spectrum, you can think about regression models that don't really care about explaining how x's relate to y's, but care a lot more about how the model overall predicts your outcome. Okay, and so kind of on the other end of the spectrum, I would argue from econometrics is more in the sort of machine learning area where we want to focus more on predictive outcomes as opposed to causal inference. And that is going to be reflected in the types of approaches that that whole world of modeling uses. And we're going to start talking about that today. Okay, so notice that all of this causal stuff, we are still running these like linear regressions, right? And we're doing kind of nuanced things with them, but we maintain linearity because actually it's really easy to interpret linear models. But as we think about moving beyond linearity, so as we move away from linear models, we lose interpretability. But we gain predictive power. Predictive power and flexibility in fitting models. Okay. So we are going to talk about a whole kind of evolution of regression. We're going to talk about polynomial, stepwise, how this goes to thinking about something like splines, and then we're going to think about the comparison to local regressions, and then bias, and how this relates also to general additive models. Okay, so there's a whole set of things we're going to start looking at as we depart farther and farther away from linear models. So we've actually, I think at some point we talked about this, right? So for a polynomial model, right, this is the idea of I have yi equals beta 0 plus beta 1 xi. I'm going to go to something like this. Beta 0 plus beta 1 xi plus beta 2 xi squared plus beta 3 xi cubed and so on and so forth. Beta n x I to the n plus my error term. So adding in these extra terms allows your fit to become more and more flexible, and that can like take on strange shapes near boundaries of x. Okay, and so let's jump back over to R. Take a look at a linear model. Okay. We are going to. Okay, I'm kind of copy and pasting this bit, but yeah, you guys should be somewhat familiar with this at this point. So we're going back to our synthetic data, so x, random uniform, 1000. I'm going to generate 1000 points between 0 and 5. There's going to be this deviation or error, and that's going to be normally distributed, 0 to 0.2, and then y is going to be a little bit of a crazier function now. Okay. So what does this look like? This looks something like this. And I'm actually going to make the color gray. No. So we're gonna do a pretty non-linear looking model now, okay? So this is like some kind of sinusoidal thing that's like increasing. Okay. So let's do a linear model, lm y on x. Okay, and let's plot that. Something like this. And actually, I'm going to superimpose the actual function. So this is something you normally wouldn't see, right? This is like, because we made it, so we can actually say what this looks like. So here's the actual curve. This is the true function. And our regression looks like this. Okay, so that's our linear model compared to the true function. Okay. So I can actually add in x squared plus x cubed plus x fourth using this function called poly. So we're going to do this. So this model here gives me x to the first power, x to the second, plus x to the second power, plus x to the third power, all the way up to x to the 25th power. So we have just added a whole ton of polynomial terms into our model. Okay, I can find my mouse, there we go. And I'm just gonna predict using this model across the x axis, so x equals sequence from equals 0 to equals 5, y equals 0.01. Okay, run this thing and let me plot it as a line, which should give me sorry. So let me copy and paste this. Okay, so where am I? Okay, let's add that line. Lines x equals sequence from 0 to 5 by 1. Okay, so you guys can see what happens when I run 25 polynomial terms for my x. Yeah, look at that. I'm actually like a lot closer to this dotted blue line compared to the red line, right, of our true function. Yeah, and so this is kind of the power of the adding extra polynomials. You get all this extra flexibility, which lets my line do this kind of thing. Okay, this is a very common drawback of polynomial models, is at the edges, these things get like crazy. It's difficult for these to kind of align with the data because, yeah, at the extreme ends of your polynomial, you get a lot of crazy terms that leads to something like this. Okay. Okay. Questions?
Is there like a similar concept of bias variance?
Yeah, okay, so what would that question be? The question, I guess, would be, how many polynomial terms should you use? And so how do we determine that?
Cross-validation.
Cross-validation, yes. Exactly. So you could do cross-validation to figure out what's the right number of polynomial terms to minimize the out-of-sample predictions. Prediction error. Great. Now, let's think about a different technique.
Is there something besides the polynomial model?
Oh yeah, we're gonna talk about that right now.
Okay.
We're gonna talk about a whole bunch of these things. What's another way we could do? What's a different way we could do a nonlinear mapping? So piecewise, also known as a segmented regression. So here we talked about how we are changing y equals beta plus beta 1 x to y equals beta 0 plus beta 1 x plus x squared plus x cubed and so on. What about if we do something like this? Y is equal to beta 0 plus beta 1 xi plus epsilon, and we split it, so you have yi equals beta 0 plus beta 1 xi plus this for xi less than a breakpoint, bp, and then you have yi equals beta 2 plus beta 3 xi plus error for xi greater than bp. What does that mean? It means if I have some points that look like this, instead of running a regression that would net me, different color, right? Instead of running a regression that would look like this, I set up a breakpoint and I run 2 linear regressions. Then one regression goes like this, and then one regression looks like this. Not too complicated, right? Okay. So we can do that. We're gonna use, oh, sorry, yes, go ahead.
I'm just curious, what would be the benefit of breaking it up like that? Like if you have a gap in the data?
We're about to find out. Okay. So we're gonna use a library, a package called segmented. And we're gonna run a piecewise model using, so actually the way this works is you use this function segmented and we actually put in the model, the linear model that we set up already. And what it does is all you need to do is specify breakpoints, seg.c, which you define as psi. And I'm just gonna add in a whole bunch of breakpoints from 0.5 to 4.8 in increments of 0.2. Run this guy, and then piecewise dot predict piecewise dot model new data is equal to, I'm just gonna copy and paste the thing from before. We're predicting over the same new data. So something like this. Okay. And I'm going to copy and paste my plot. Where's my mouse? There we go. And to this, I will add the predicted line from this thing. Actually, I'll just, it'll be exactly the same as the line above, except you're using the piecewise prediction, and I'll use a different color. Okay, so if I add this in, okay, so your question about why we would do this. So dotted blue line is our true function. compare that against our red line. So the new one, let me make this a little bit bigger. And actually, let me just do it like this. Let me leave out the exponential one for a second. Okay. So what have I done? I've added all these breakpoints, like here. I've added a bunch of breakpoints so that I'm running a little linear regression, another little linear regression, another little one. So which one is closer to the true function, the red line or the orange line? Orange line. That's why. Yes, so piecewise linear can actually give us flexibility to adapt to a whole bunch of or really nonlinear things with a linear model. Okay, here you can still, so going back to the like interpretability and like the causal versus predictive stuff, right? In the polynomial one, you're gonna have a beta for your x1, a beta for your x squared, a beta for your x cubed, and it's like, are you really gonna interpret all of those betas? Like, what do those betas even mean, right? Here, okay, I guess it is still more interpretable because for like this segment here, there's a beta, and I can tell you that like the slope from x is 0.6 to 0.7 is like negative whatever, negative 0.3 or something, right? But like you have so many slopes to interpret if you have lots of breakpoints. So the interpretability part is like kind of less interesting, and people don't really do that. Okay, so that's our linear segmented one, and then if I add this back in, you can see how that compares against the polynomial one. Which one do you guys like better? Polynomial or segmented? Segmented? Okay. And maybe you like that because it's closer in some regards. Kind of depends on how many polynomials you add to it. This is like an arbitrary number. Yeah, okay, but so what is one of the drawbacks of the segmented regression?
Interpretation.
Well, interpretation for everything that we're talking about at this point, so yeah.
I had a question about the segmented approach.
Yes.
Which might be a drawback of others, which is how do you decide where to put the breakpoints?
Yeah, yeah, I kind of glossed over that, didn't I? So there's two parameters to think about with segmented. It's the number of segments and the location of the segments. How do you think you would determine these things? Cross-validation, yes. Yeah, so you could experiment by putting breakpoints at many different places, and you can also experiment by adding more or less breakpoints. Yeah. Sorry?
I'm asking, I didn't want to interrupt you. It's number of segments and
Yeah.
what's the other criteria?
Number of segments and the location of the segments, right? Like your choice to put a breakpoint in a particular place, right? Cross-validation. So you're kind of pointing to one that I wasn't thinking of, but yeah, like the complexity of doing the cross-validation for segmented is actually a little bit harder because you have two parameters and that can like explode what you want to look at in cross-validation. Okay, but another drawback is like you have these kinks, and it's very hard to get smooth lines with segmented regressions, whereas this kind of naturally happens in polynomial. So yeah, it would be hard to replicate smooth shapes with segmented regression unless you had lots and lots of segments, but sometimes you run into issues of like overfitting, right, when you do that. so why not both? Okay, so the next step is to think about trying to take advantage of the strengths and weaknesses of both and actually combine them. So let's look at what happens if I do both polynomial and segments together. Okay. So in fact, we have a name for this. This is known as a spline, which is piecewise polynomial functions. Parentheses plus a bit more. And I'm going to show you what I'm talking about in just a second. Let's suppose that I have some data that looks like this. I'm gonna do something like this. Okay. Let's have a breakpoint here. So this is my breakpoint. And if I fit this with a cubic regression with 2 segments, I might get something that looks like this. Okay? So this would be known as a piecewise cubic. So you have 2 cubic, right, so polynomial regression line segments. Okay, same thing here. So I can add in another constraint that says, okay, I don't want there to be a disconnect at the breakpoint. Let's make it continuous. Okay. So this would be, okay, let me draw the lines first. So this might look something like, whoa, don't do that. Why are you doing that? Okay, hang on. Something like that. So this would be known as a continuous piecewise cubic. So this is plus additional constraint that lines must touch. Okay. And the last one is we're going to ask it to do one more constraint. Which is that the lines have to be smooth at the breakpoint. So now this might look something like this. And this is known as a knot. It is a breakpoint with a set of constraints that enforce that the lines must touch and they must be smooth. So this is known as a cubic spline. So this is plus additional constraint that lines must be smooth. And that is, so technically this is done by doing first and second derivatives are continuous at your breakpoint. Okay? Alright, so kind of backing up a little bit, we are building up in kind of logical complexity, right? So we think about polynomials, we think about stepwise, and then we think about combining them together to get kind of the strengths of both, while kind of negating some of the weaknesses of both as well. When you do that, you often end up with something that looks like this. And so in order to kind of smooth that out, they add these two extra conditions that at the breakpoints, lines must touch. At the breakpoints, the first and second derivatives are continuous, which makes it look smooth. Yeah?
What do you mean by continuous? Like equal or
Yes. The first and second derivative have to be the same at that point. That way, the slope of the line, right, like the slope of the line here and the slope of the line here are different, whereas here, technically they're like right at that point, they should be the same. Okay, so this ends up looking like yi equals beta 0 plus beta 1. You have what's known as a basis function. This is the thing that's kind of like transforming the fit. We're not going to go into the technical details behind this. But like, you can imagine that these basis functions that transform x in certain ways are actually fairly complex. And so the betas no longer really mean anything interpretable. And so we don't think about looking at betas for spline functions really. Okay. Now, so what are the things that you can vary for increasing or decreasing complexity for a polynomial? Number of polynomials, exactly. Okay, and then in a segmented regression, what are the things that we can vary? Two things. Yeah, number of breakpoints and location of the breakpoints. So now we're in spline world. Spline world, we can do the number of polynomials, the number of knots, and the location of the knots. Too much flexibility. And it turns out you don't need to. So actually, with just a cubic spline and then an arbitrary number of knots, you can make your line do almost anything, okay? And so it's pretty common to just do a cubic spline. Cubic splines are the most common. And we trade off the polynomial flexibility. So this is having x to the n terms for knots. So imagine that I have some set of points here. Okay. If I can copy and paste these. Alright, well, we'll do this manually. Okay, so it'll end up looking something like 0 knots, and if I have like 1 knot, and then 2 knots, maybe it'll be something like this. Okay, so the idea is that I have more like squiggliness, flexibility, the more knots that I add. Okay? How do I choose the number of knots? Cross-validation, yes. Alright, so alright, one moment here. So we're gonna use library called splines. Okay, I'm just gonna copy and paste because this is a lot of manual typing here. You can don't have to like follow along typing. You'll be able to look at this in the notes later. So in the splines package, there is a function called BS, stands for basis. So what variable you're doing a basis transformation on, which is x, so y regress on transformation of x, and the knots, you basically just tell it where the knots are. And this will, if you do this, you're kind of saying both location and number, right? Because you're telling where the knots are. So I'm gonna run 4 different examples of the cubic spline. And what I'm doing here, so in the first one, I'm adding a knot from 0 to 5 in increments of 1. So in the plot here, I'm putting a knot here, a knot here, 1 knot here, 1 knot here, 1 knot here, and 1 knot at the end. And this is, once I run that model, I'm gonna predict x's from 0 to 5 to see essentially how my model does, and then I'm gonna generate a prediction much like these green and orange lines, and we're gonna compare. So then, cubic spline 2, second example, I'm gonna do exactly the same thing, except this time, I'm gonna have more knots. Instead of here, 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 and here, in increments of 1, I'm gonna go with the increments of 0.5. So not here, not here, not here, not here, and so on. And then predict 3, I'm gonna do knots in increments of 0.1. And then in the last one, model 4, I'm gonna, oh sorry, in 0.3, and then in the last one, I'm gonna do in increments of 0.1. Everyone following along? Questions? Okay, so let me run all of this. Yeah, I'm getting a couple warnings here because actually like it gets a little weird if you have like knots really close to the edges and depending on how they're spaced out. Don't worry about that. This is just to see what happens. Alright. So here's our points again. Let's see. This is, oh, I put the standard errors in here. Okay, forget this. Don't need to worry about these guys. Okay, when I have less knots, what do you guys think guys think the regression line will look like? More squiggly or less squiggly? Less, okay? So let's see. So that is with a total of 5 knots, okay? And cubic, right? So all of this is cubic splines. Now let's see what happens when I increase the number of knots. So double the number of knots. Okay. Getting a little bit more flexibility, but not much, right? At the ends we do, right? And again, that has to do with the weird stuff that polynomials do at the sort of ends. And in fact, we can see, yeah, and over there. Let's keep going. Boom, okay, so with knots at every 0.3, you can see the orange line is much closer. And green. Okay? So, yeah, hopefully you guys can see. And let me add in the original, the true value. Yeah, so hopefully you guys can kind of see the power of splines here, right? So we saw that the segmented regression was actually really close, but it had those kinks. But here, look at how closely we overlap in terms of the true value, black, versus the spline, right? The places you're kind of off the most, it's like over here, there's a little bit of gaps, but for the most part, right, a spline, the flexibility of a spline, of spline regressions is actually very powerful in being able to fit highly nonlinear functions. Okay. Let me add one more little thing here. Let me keep adding more knots. Okay, so now I'm going in much smaller increments. So let's see, there's gonna be in the fourth model that we added, it was in increments of 0.1, and there were across 5x from 0 to 5, so there's 50 knots. Here, let's see, there's 4 to 0.01, so 4 times 5, 20, 200 knots, something like that. There's a lot more. There's a lot more knots here. No, more than that. 2,000. No, 4. Okay, I'm not gonna do mental math up here in front of everyone. There's a lot more knots here. What do you think is gonna happen? No ideas? What?
It'll be too squiggly.
Too squiggly, yes. Yeah, love it. Okay, so actually, is that a typo? I think that's a typo. That should be 5, right? Okay. Yeah. Probably too much. Actually, that's even more than I was intending. Let's try this. Yeah, there we go. Yeah. So, too many knots, right? And so, it's looking at all the like very close by points and getting influenced, right? Because you have knots that are like very close together, and you're allowed to be super flexible. So this would be an example of like overfitting, right? Because we know that you are, if I were to like randomly leave out points and do out of sample testing, right? The errors for all of these like little deviations is actually bigger than the one where we have fewer knots, right? So that is why cross-validation is important for us to be able to say something about how many knots to use and where to put them. Okay, any questions? All right. So we saw actually with a small number of knots that the curvature of the lines at the endpoints were still really kind of large. And that is the product of the fact that they're still using these polynomial functions. And actually what that ends up doing is you can lead to, like very high standard errors and also like weird things happening at the boundaries. So There is an evolution from these cubic splines to something called natural splines. And this natural splines, all they do is essentially make the last bit linear. So instead of doing a cubic function, the ones on the edges are linear. And there are constraints that essentially let you do that. And so natural splines are arguably a better way of doing some of these things. And actually, from a logistical standpoint, running that in R is actually even a little bit easier. So let me show you guys what that looks like really quick. So instead of the BS function, you use the NS function, standing for natural splines. And here, one of the nice things is that I can just say df equals, and that will specify the number of knots for you. So you don't have to do this whole sequence business, and this will space them out evenly. But you do have the option of putting knots at specific places if you want. But since I'm just spacing them out equally, then it makes no difference here, and in fact, it's a lot easier for me to just say df equals 10, right? Okay, so this is, again, we're doing this like progression, right? Polynomial, stepwise, both are good in some ways, but bad in some ways. So then we go to cubic splines, which is kind of an improvement from both of those, into natural spline, which is an improvement over cubic splines. And let's do this. Okay, so I'm doing the same thing as before. Spline, the prediction for the spline, and then adding more knots in each progressive model. And again, we can see what happens with all of this. And let me plot these guys very quickly. Okay, so here we go. Natural spline with 10 knots, natural spline with 15 knots, natural spline with 30 knots. Okay? And here, it's a lot easier, again, when you do cross-validation to select the number of knots, then you can just put it into this df thing here. And we can look at an example of overfitting, right? I can do 300 knots. Run this guy, and we get that too much squiggliness again. Okay. Questions?
This might be a stupid question, but the function that we made was like a combination of cosine and sine. Do we have any models that we can use that are like trigonometric like this? Or is it, because like in a lot of cases, like weather data and stuff is kind of like a sinusoidal pattern. But is it just better to always be using like splines and things like that? Is it not even worth attempting to like find this sine function that?
Oh, yeah. Okay. this is a important, like, philosophical thing that you're talking about essentially, right? Because we do like a linear regression when the like functional form is linear. So if I were to run a spline regression or polynomial regression or piecewise segmented regression on something that is truly linear, it will never do better than a linear model, because the linear model like fundamentally assumes that like the best fit is aligned. And the other models might get like befuddled by variations in the data. So then the question is, okay, if there's something that's like truly like a quadratic function, or something that's like truly a exponential function, like we could figure out what the functional form is and like write it as like beta of x squared or beta of log x, and those models will always kind of do the best for that. And you are asking about, okay, what if you have like weather data that's like sinusoidal? There must be some like true function that describes that shape. And maybe not. I don't actually know. But the problem is there could be so many different types of functions out there in the world that we can fit data to. It's like very hard to figure out what that function is. Like you could, a lot of times you truly would never be able to extract like what the true function is. And so these models come about as a flexible way of fitting those things without necessarily replicating the like true functional form, right? And so in this example, right, like if we were to do, I think what you're essentially describing, then what I would want to do is, oh, no, not up here, here. Yeah, I would, have to do something like sine, I would have to figure this out, right? Sine x cosine beta x plus, so beta 1 x plus beta 2 x. So this is the functional form of what I made up. And then the parameter values that I solve for would be 10 and 0.5. Those would be my betas. But like, I have no idea how I could come up with this functional form from like looking at the data, you know what I mean? So instead, we'll just generically do this like super flexible thing that can fit the data, but isn't gonna tell us anything about the functional form, right? So nowhere in the splines do I say anything about like a sine, cosine, multiplication thing, right? Does that make sense? Yeah. Okay. But wait, there's more. We're not done with splines yet. Okay. So I'm gonna minimize residual sum of squares. And in our spline world, we are doing something like this. So minimize the sum of y minus gxi squared. This is like our basis function thing, right? And so this is going to tell us the error, right? Our prediction minus where the actual thing is squared. So this is our residual sum of squares, total error term. So where g of xi is the spline cubic function that constrains the first and second derivatives to be continuous. Okay, so, right, this like, I kind of glossed over this idea, right, but the continuity in the first and second derivatives at the knot. So let's actually play around with that a little bit. So, suppose you have a knot at every single point. That is going to let us do something like, so if I have, you know, a bunch of data points like this, essentially what I'm saying is, let's literally have one knot at every single x. So I can be super, super flexible, and you know, I can pass through all of my points like so. So this perfectly minimizes RSS, right? Because my error is 0, right? We've seen this kind of concept a couple times now. But what's the problem here? We might be overfitting, yes. But you have overfitting. Okay, so let's do something a little bit interesting here. So I'm going to minimize this guy. Same as before, but this time I'm going to add this term here. So this shrink the second derivative. Does this look like anything that you guys have seen before? Maybe. This is known as the tuning parameter. And this is known as our penalty function. Yes, yes, exactly. This is basically analogous to the ridge regression. Great. So, if you think of the second derivative as like smoothness, right? the second derivative is the rate of change of the slope, I can, like in a ridge regression, have a penalty on the second derivative that encourages smoothness so that the rate of change of the slope can't be big. So even though you have lots of knots, right? So let me do some rough example of this. Okay, so if I have 3 points that look like this, right? I could fit through these points like, whoa. Okay, let me. Okay, something like. No, okay, hang on. It's kind of hard to do this example. Okay, maybe I'll do something like this. Versus. So there's like multiple ways that I could fit through a set of lines. I'll just draw the example that I actually drew in my notes. So. In one case, I might have a super flexible thing, whereas in another case, I might have something like this. And so this is low tuning parameter and a high tuning parameter, right? So if this term is 0, then it just returns to the original one, and I have a knot at every point, and so I'm super, super, super flexible, and I can do things like this. When the tuning parameter is high, there's a penalty function that says if my second derivative is large, then this whole term will increase, and I kind of want to minimize that, right? So what does the second derivative allow me to do, right? So the change in the slope goes up and down, and so even though I have a knot at every single point, the ability of the slope to change rapidly is decreased because of this penalty function. Does that make sense to everyone? Any questions about this? Right, so this is a kind of different way of viewing the spline part of it, where instead of trying to mess with the number of knots and location of the knots, this just says, okay, forget trying to make that decision. Like, the parameter that we're going to be messing with is just this tuning thing, and we're going to have a knot at every point. So this is, I think, a lot easier to do something like cross-validation on, right? Because you're literally just varying your tuning parameter. Okay, questions? Yeah.
Then how do we find the best tuning parameter?
I don't know. How do we find the best tuning parameter? It's the same answer for all the questions I've been asking you guys. Cross-validation, yes. Right, and so that's our golden ticket for figuring out the balance between overfitting and having your, high bias model. Okay. All right, so jumping over to here. This one's even easier to do. Alright, all the way down. Okay, so it uses a function called smooth.spline. Okay, you put your x's in, so the function, you have to define your x's, you have to define your y's, and then s parameter, that is the value of the tuning parameter. And let's see what happens. Okay, so here's our points again. S parameter is equal to 1. So more smooth or more squiggly. Right, so when we have the tuning parameter is very large, you have a large penalty function on the ability of your thing to be squiggly, which means it's going to be more smooth and less squiggly. Okay? So high penalty function on the second derivative. So not allowed to change slope rapidly. There. Okay? We'll decrease the penalty function and allow the line to change slope more rapidly. There. There. And there. There. So this is like a nice example where I can kind of visually see like underfit and overfit, right? So if I do this again, actually let me add in the original dude again, just so we can see how it overlays. Here, and let's make the color purple. Okay. Alright, so there's our true function. What do you guys think? No good? Keep going. Okay, red line. Okay, so the green line, when we have our penalty term at 0.5, looks pretty good, right? Even in that area where you have problems on the cubic spline, it looks a lot better. Yeah, and at the edges, it's still pretty good. 0.25 penalty, so even more squiggly. Not bad still, but maybe it's harder to see from over there, but I can see some deviation, some squiggliness, particularly over here. It's kind of going up and down a little bit. It doesn't look visually as good as the green line. And then the black one, right, you can visually see too much squiggliness. Okay, so that's the visual way of doing it, but right, the way that we quantitatively, more rigorously do this is via cross-validation. And that's our way of determining which penalty parameter to use, or tuning parameter to use. Okay. Couldn't get through everything today, but that's all right. We'll continue on some more nonlinear stuff next time. Okay. I'm gonna end here. We're not gonna get into the GAM stuff yet. Any questions about this? or questions about homework projects, I'll stick around a couple minutes if folks wanna chat about that. Yeah. Did you have a?
Maybe, yeah, for the cross-validation technique right here, what
Yes.
we are going to do, but we're not just visually looking at which are the best fit.
Yeah.
We're looking for them specifically the minimum value of,
The error, of the outer sample error.
yes.
Oh, sorry, there is an automatic way to do that. So in SP model, the nice thing is, okay, you can use the function that I talked about, but I can also, instead of specifying the parameter value, I can just say CD equals true. And it will do the cross validation for you. Yeah.
Oh, wow.
Yes,
That's wonderful.
Yeah.
yes, so this, yeah, this will do this for you, and in fact, okay, one sec. I can do this, and we can see what that looks like. And that's like the best that you can yeah, so it's overlaid on top of the true model. Yeah. So, splines, they're great, very powerful.
For the funnel project, are there any examples on Canvas? Or will there be?
Yes, I can do that. I will put some projects from previous years, and you guys can see, yeah, what they look like. Yeah, can you email me to do that so I don't forget?
Okay, sure.
Thank you.